Now we're going to talk about combinations, which are distinct or different from permutations in the area of ordering. An R combination could just as well be called an R collection. I'll go ahead and write it here, although we're not going to use that term, but they both start with C, so that might be helpful. Because an R combination is just a collection of R things chosen from N distinct objects. Now, collection is probably more natural in our typical day-to-day language, but the term that virtually everybody uses for this is R combination. So to distinguish it from permutation, where you have ordering that really determines or distinguishes permutations, maybe thinking of this as an R collection will be helpful. Ordering does not distinguish them here. They're just a bunch of things plopped on a table, say, and it doesn't matter how you arrange them there. And R combination is a collection of N distinct objects. A collection of N distinct objects is a collection of R of them. Yeah? You could think of it in set language, and our combination of a set of N elements is a subset containing exactly R of the elements. Sets aren't distinguished on the basis of order, so the same is true of and the same is true of combination, so the two things are the same. We have a symbol for the number of R combinations of a collection of N distinct elements. It's denoted by CNR, I wrote that wrong. N over R, no dividing line there, just N over R inside the parentheses. And we'll come back to that notation and describe why it's used and where. If we look at the number of 3 combinations of a set of 4 objects, there are only 4 of these, different collections of 3 of them chosen at a time. An easy way to see that is if you're going to get a 3 combination, just 3 of the letters, you leave 1 behind. There are 4 to leave behind. So there are 4 combinations we get there. Now the thing that's interesting about this too is if we write those down, A, B, C, A, B, D, A, C, D, and B, C, D, those 4 different things, each pair of them differ because they don't have the same letters. We could form from this permutations. So here are permutations: A, C, B, B, C, A, B, A, C, C, A, B, C, B, A. So this is one object, and there are 3 factorial permutations of those letters from that one combination. The same thing is true here. We'd have A, ADB, yeah, that's okay. Then BAD, BDA, the 2 that start with B, and then DAB, DBA. Also 3 factorial here. There will be 3 factorial here and 3 factorial here. And you may remember that's how we wrote this down earlier. If I can scroll back up here, and I know this might be a little annoying, so hang on until I get back there. I'll just scroll back up there and point out that place where we did this, where we list all the permutations. But this all corresponded to ABC, this to ABD, this to ACD, and this to BCD. So for the 24 permutations, 3 permutations, we only have 4 combinations that correspond to it. And where do the 4 and the 24 relate? Well, each of the combinations can be permuted 3 times because it's a 3 combination, and each combination permuted 3 factorial times, I should have said, would give us 4 times 3 factorial, gives us all the permutations. 4 times 3 factorial is equal to 4 factorial, and this is P 4, and this is C 4, 3. This is for 3 times 3 factorial. That works generally. Each combination, our combination, each R combination can be permuted or arranged or ordered in R factorial ways. So CNR times R factorial will just be all the R permutations. That's how we could get all the R permutations. So that's a nice arrangement or relationship between the two right there. Okay, we have a number of corollaries, and I think I will hold off on those till the next time. But in class we'll make use of the basic properties that we've already discussed.